Hello there, and welcome to the Sleepy Science Channel. Tonight, we'll be exploring the greatest story ever told. The timeline of our universe is one of science's greatest discoveries. From the first moments of cosmic history to the distant future still waiting beyond our view. It is a story written in light, gravity, matter, and time. The universe is not a still place. It grows, it changes, it builds stars and shapes galaxies, and it turns simple ingredients into worlds that can host the miracle of life. Some parts of this story are measured with astonishing precision. Others remain among the deepest mysteries in science. As we travel through it, we will follow the rise of structure from the earliest universe into the vast cosmic web we see today. We will meet forces that bend light, objects that warp time, and questions that we might never answer. If you enjoy these curious journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is settle in. Let your shoulders relax and notice your eyes grow heavy. And as your mind begins to gently unwind, join me as we explore this cosmic story together. Let's begin. The universe began everywhere at once, not from one point. It is tempting to picture the beginning as a blast in empty space, like a spark appearing in a dark room. But that picture misses the deeper mystery. There was no empty room waiting around it. According to modern cosmology, the beginning happened throughout space itself, because space was part of what was unfolding. Every region we can observe today was once packed into an incredibly hot, dense state, and every direction carried the same early history. No telescope can look outward and find the birthplace as a special location. Wherever you are in the cosmos, the story begins with the same ancient expansion. This means the center is not hidden in some remote galaxy. It is not beyond the edge of our instruments. In a real sense, every place was once part of that first beginning. The ground beneath you, the air around you, and the farthest galaxy all share that same origin. Space itself is expanding, carrying galaxies away from one another. When astronomers say the cosmos is expanding, they do not simply mean galaxies are flying through a fixed emptiness. The deeper idea is stranger. The distance between distant galaxies is increasing because the fabric between them is stretching. A galaxy can sit almost calmly within its own neighborhood, yet over immense distances, the space separating it from another galaxy grows larger with time. This is why faraway galaxies appear to recede from us, and why the most distant ones seem to move away fastest. Their motion is not like shrapnel from an explosion. It is more like the scale of the universe changing beneath everything. Light traveling across this growing space is stretched along the way, shifting toward redder wavelengths before it reaches us. That stretched light is one of the great clues that revealed cosmic expansion. The universe is not a stage where events happen. The stage itself is changing as the story continues. The oldest light in existence still fills the sky today. Long before there were stars, the universe glowed with trapped radiation. Light existed, but it could not travel freely because charged particles kept scattering it again and again. Then the cosmos cooled enough for electrons and nuclei to join into atoms. Suddenly, space became transparent, and light began moving almost unhindered across the growing universe. That ancient glow is still here, arriving from every direction as a faint microwave signal. It is not visible to our eyes, but radio telescopes can detect it with remarkable precision. This radiation gives scientists a baby picture of the universe from an age before galaxies had formed. Tiny differences in its temperature reveal where matter was slightly denser, and those slight differences later grew into enormous structures. It is astonishing to think that the sky is filled with a fossil glow older than every star we can see. We are surrounded by the afterglow of cosmic childhood. Nearly everything in the universe is invisible to our telescopes. The stars, planets, gas clouds, and glowing galaxies we observe are only a small fraction of what seems to exist. Most of the cosmic budget is hidden from direct sight. One part is dark matter, which does not shine or absorb light in any ordinary way, but reveals itself through gravity. Without it, galaxies would not spin the way they do, and galaxy clusters would not hold together as strongly as they do. Another even larger part is dark energy, a name for the unknown influence that appears to be speeding up cosmic expansion. Together, these unseen components dominate the large-scale behavior of the universe. This does not mean they are imaginary. It means their presence is inferred from effects that ordinary matter cannot explain. The humbling truth is that astronomy has mapped breathtaking beauty across the sky, yet most of reality remains hidden. What we see is only the illuminated surface of a much deeper puzzle. Every atom in your body was forged by ancient stars. The early cosmos made mostly hydrogen and helium. That was not enough to build bones, blood, oceans, or living cells. The heavier ingredients had to be manufactured later inside stars and released through stellar death. Carbon formed in aging stars. Oxygen came from massive stars. Iron was produced in the final stages of stellar evolution and in explosive events. Even rarer elements needed extreme cosmic violence to appear. Over time, dying stars scattered these materials into surrounding space, enriching clouds of gas that later collapsed into new stars and planets. Our solar system formed from such recycled material. This means the chemistry inside you has passed through older chapters of cosmic history. The calcium in your teeth, the iron in your blood, and the carbon in your cells are not merely earthly substances. They are ancient stellar products, assembled by physics long before Earth existed, then gathered into a living body capable of wondering about its own origin. Black holes can slow time near their edges. Near a black hole, gravity becomes so intense that it changes the pace of time itself. This is not just a metaphor or a science fiction trick. It follows from general relativity, which shows that gravity and time are woven together. To an observer far away, a clock lowered toward the boundary of a black hole would appear to tick more slowly. The closer it came to that boundary, the stronger the effect would become. For the falling clock, time would still feel normal locally, because everything nearby would slow together from its own point of view. This difference between observers is one of the strangest features of the universe. It means time is not a universal rhythm beating the same everywhere. It bends according to gravity, motion, and position. Around black holes, that truth becomes dramatic. The edge is not a solid surface, but it marks a place where escape becomes impossible and time itself behaves differently. The universe was once too hot for atoms to exist. In its earliest stages, the cosmos was not filled with familiar matter. It was a searing mixture of particles and radiation, so energetic that atoms could not hold together. Electrons moved freely instead of settling around nuclei, and light was constantly knocked off course by charged particles. Métis was not arranged into stars, planets, dust, or chemistry. It was more like a brilliant, dense plasma, ruled by heat and rapid interactions. Only after the universe expanded did its temperature fall enough for stable atoms to form. That cooling changed everything. With electrons finely bound to nuclei, light could stream across space, and gravity could begin shaping matter more effectively into future structures. The world we know depends on that transition. Without atoms, there are no molecules. Without molecules, there are no rocks, oceans, atmospheres, or cells. The familiar universe emerged only after the cosmos became cool enough for matter to take its first lasting forms. Galaxies are still growing by swallowing smaller galaxies. A galaxy may look peaceful in a telescope, but its history is often built from capture and disruption. Large galaxies grow by drawing in smaller companions with gravity. As a small galaxy falls inward, tidal forces stretch it apart, pulling stars into long streams that can wrap around the larger system. These faint trails are like archaeological evidence written in starlight. They show that galaxies are not finished objects. They are evolving structures, assembled piece by piece across immense spans of time. The Milky Way has absorbed smaller galaxies before, and it is still interacting with dwarf companions today. This growth does not usually happen like a sudden collision between stars. Space inside galaxies is so vast that individual stars rarely crash. Instead, gravity rearranges orbits, reshapes gas, and changes the structure of the whole system. A galaxy is not only a collection of stars. It is a record of everything it has gathered. The future of the universe may be dark, cold, and endless. Cosmologists study not only where the universe came from, but where it may be going. Current evidence suggests expansion will continue, and distant galaxies will drift farther from one another. Over vast stretches of future time, star formation may slow as gas is used up or locked away. The brightest stars will die first. Smaller red stars may shine for unimaginably long periods, but even they will eventually fade. Galaxies could become filled with stellar remnants, dim planets, black holes, and cold debris. If expansion keeps accelerating, faraway regions of the cosmos may become forever unreachable, leaving each surviving galaxy group increasingly isolated. This possible fate is often called heat death, though it is not a fiery ending. It is a gradual loss of usable energy and contrast. The universe would not vanish in a dramatic moment. It would continue thinning, cooling, and fading, carrying time forward into a future almost beyond imagination. We can see billions of years into the past with light. Astronomy is a form of time travel because light does not arrive instantly. When you look at the moon, you see it as it was moments ago. When telescopes study nearby stars, they see years into the past. When they collect light from remote galaxies, they are receiving messages that began their journey when the universe was much younger. This is why deep space images are also historical records. A distant galaxy is not shown as it looks today, but as it looked when its light set out. The farther we look, the earlier the chapter we are reading. Powerful observatories can study galaxies from an age before our solar system existed, and some from times close to the dawn of galaxy formation. This makes the night sky more than a view across distance. It is a layered archive of cosmic history, where every photon carries a timestamp from the place it left behind. The Big Bang was the beginning of space-time itself. The phrase can make the beginning sound like an explosion inside a pre-existing void. The scientific idea is much deeper. It describes an early state when the universe was extremely hot, dense, and rapidly expanding. Space was not a container sitting outside the event. Time was not a separate clock already ticking beyond it. In our best models, space-time is part of the universe's physical structure, and the earliest moment we can describe marks the limit of those models. Asking what happened before may not have a simple meaning, because ordinary time may not extend cleanly past that boundary. Scientists can trace the expansion back with great confidence to extremely early conditions, but the absolute beginning remains linked to unresolved questions about gravity and quantum physics. This makes the Big Bang both a powerful explanation and a frontier. It tells us how the observable universe evolved from a hot, early state, while still pointing toward deeper unknowns. Time may have started when the universe began expanding. We often imagine time as a line that stretches endlessly backward. Cosmology challenges that instinct. If time is part of space-time, and space-time was once in an extremely compressed early state, then the question of a time before the beginning becomes surprisingly difficult. Some theories suggest that time itself emerged with cosmic expansion. In that view, there was no earlier ticking clock waiting for events to happen. There was no empty duration sitting outside the universe. The beginning would be the origin of the very framework that lets before and after make sense. This does not mean every mystery is solved. Physicists still explore ideas involving quantum gravity, bouncing universes, and deeper structures beneath ordinary time. But even the possibility is astonishing. The flow you feel in every heartbeat may be connected to the same cosmic unfolding that shaped galaxies. Time is not merely a background. It may be one of the universe's oldest creations. The newborn universe was smaller than any galaxy today. In the earliest moments we can meaningfully discuss, the region that became our observable universe was compressed into a state of extraordinary density and heat. It was not a little ball floating inside space. Rather, all the space that would later stretch into our visible cosmos was once packed far more tightly than it is now. Comparing this beginning to a galaxy is almost misleading, because galaxies themselves appeared much later. Still, the contrast helps the mind approach the scale of cosmic growth. The stars of the Milky Way now spread across a vast disk of light, yet the material and space tied to our cosmic horizon began in a condition unbelievably smaller and hotter. From that compact state, expansion carried regions apart, lowered temperatures, and allowed structure to emerge step by step. The grandeur of today's universe began from conditions so extreme that ordinary intuition fails. Everything large started from something almost impossibly dense. Inflation may have stretched the universe faster than light. One of the boldest ideas in cosmology is that the infant universe experienced an incredibly brief surge of expansion. During this episode, space itself may have grown at a staggering rate, smoothing the cosmos and stretching tiny fluctuations across enormous distances. This does not break the rule that objects cannot move through space faster than light. The rule applies to motion through space, while inflation concerns the expansion of space itself. The theory helps explain why the universe looks so uniform in regions that seem too far apart to have exchanged signals in the usual way. It also explains how microscopic variations could become the starting patterns for later cosmic structure. Inflation is not proven in every detail, and scientists continue to test its predictions through ancient radiation and the distribution of galaxies. Yet it remains a powerful idea. A fraction of a moment may have shaped the entire observable universe we see today. Tiny quantum ripples became the seeds of galaxy clusters. At the smallest scales, the early universe was not perfectly smooth. Quantum physics suggests that tiny fluctuations were always present, slight differences in density and energy, but appeared in the earliest conditions. By themselves, they were unimaginably small. But as the universe expanded, these tiny variations were stretched to cosmic scales. Gravity then gave them importance. Regions that were slightly denser attracted more matter over time. Slowly, those small advantages grew into large structures. Gas gathered. Stars formed. Galaxies assembled. Clusters collected into even larger patterns. The vast cosmic web began with these delicate irregularities. That is one of the most astonishing links in science. The largest structures we observe today may trace their ancestry to the smallest possible disturbances. When astronomers map galaxy clusters, they are not only studying where matter ended up, they are reading the magnified outcome of ancient quantum uncertainty, amplified by gravity across nearly the whole history of the universe. Matter barely defeated antimatter in the universe's first moments. The early cosmos likely produced matter and antimatter in almost equal amounts. When the two meet, they annihilate, releasing energy. If the balance had been perfectly equal, nearly everything would have vanished into radiation, leaving no stars, no planets, and no chemistry for life. But something tipped the scales. For reasons still being investigated, matter gained a tiny advantage. It may have been only a minuscule excess, but that slight imbalance changed everything. After matter and antimatter destroyed each other in vast numbers, the leftover matter became the raw material for the universe we know. Every galaxy, cloud, ocean, and living cell depends on that ancient asymmetry. Scientists search for the explanation through particle physics, studying how nature treats matter and antimatter differently under rare conditions. The mystery is profound because it asks why anything material survived at all. Our existence may depend on one of the smallest victories in cosmic history. Most antimatter vanished almost completely after the Big Bang. Antimatter is not fantasy. It is real, measurable, and routinely created in high-energy experiments and some natural processes. Antiparticles have the same mass as their matter counterparts, but opposite electric charge or related quantum properties. In the hot, early universe, particles and antiparticles were constantly appearing and destroying one another. As the cosmos cooled, creation became less common, while annihilation continued wherever opposites met. Because matter seems to have had a slight surplus, the antimatter population was almost entirely wiped out. Today, large regions made of antimatter have not been found, and the universe appears overwhelmingly matter-dominated. Small amounts still appear in cosmic rays, radioactive decay, and particle collisions, but not as whole galaxies or stars. This absence is itself a clue. The universe bears the mark of an enormous vanished partner. Antimatter once filled the young cosmos, then disappeared so thoroughly that its missing abundance became one of science's deepest questions. The first atoms formed when the universe finally cooled enough. For a long stretch after the beginning, atomic nuclei and electrons existed separately in a hot particle fog. Light could not travel far because free electrons kept scattering photons. As expansion continued, the temperature dropped until electrons could settle around nuclei without being immediately knocked away. This event is called recombination, although it was really the first widespread combination of electrons with nuclei. Hydrogen atoms became especially important because hydrogen was the most abundant element. With charged particles bound into neutral atoms, the universe changed character. Light moved freely across space, giving rise to the ancient background radiation we detect today. Matter also became better able to gather under gravity, because radiation no longer pushed against it in quite the same way. A universe of trapped light became a universe where structure could grow more effectively. The formation of atoms was not a small chemical footnote. It was the moment the cosmos became transparent. Hydrogen became the first great building block of everything. The simplest atom became the universe's most important raw material. With one proton and one electron, hydrogen is plain compared with the complex elements in rocks, oceans, and bodies. Yet its simplicity made it abundant. After the early universe cooled, hydrogen filled space in enormous quantities. Gravity pulled it into clouds, and those clouds later became the nurseries of the first stars. Inside stellar cores, hydrogen nuclei fused together, releasing energy and creating the light that transformed the cosmos. Every ordinary star spends much of its life converting hydrogen into helium. This process powers starlight, drives stellar evolution, and begins the chain that eventually produces heavier elements. Without hydrogen, the universe would have no long-lasting stellar engines. There would be no warm planets orbiting stable suns, and no later chemistry enriched by generations of stars. The most common atom is also the first great fuel of cosmic history. Helium formed before the first stars ever began shining. Most people think of elements as products of stars, and for many elements, that is true. But helium has an older source. In the first minutes of cosmic history, the universe was hot and dense enough for nuclear reactions to occur outside stars. Protons and neutrons combined into light atomic nuclei, producing large amounts of helium along with small traces of other light elements. This process is called Big Bang nuclear synthesis. It ended quickly as expansion lowered the temperature and density, leaving behind a universe dominated by hydrogen with a significant share of helium. Later, stars inherited this starting mixture. When the first stellar cores ignited, they were not creating helium from nothing in an empty chemical landscape. They were building on a primordial supply already present throughout space. This early helium is one of the great pieces of evidence for the hot early universe, because its predicted abundance matches what astronomers observe across the cosmos. The early universe had no planets, dust, or starlight. For a long time after the first atoms formed, the cosmos was missing almost everything we now associate with space. There were no rocky worlds, no glowing suns, and no drifting clouds of cosmic dust. The universe was mostly a vast spread of hydrogen and helium, cooling slowly as it expanded. It had the raw material for future wonders, but none of the structures had appeared yet. Gravity was already at work, pulling slightly denser regions inward, but the process took time. Gas had to gather, compress, heat, and collapse before the first stars could ignite. Until then, space held potential rather than spectacle. This is one of the most powerful ideas in cosmology. The universe did not begin already rich and beautiful. It had to make its own complexity. Every planet, every crystal, every living cell came later, after gravity patiently turned simple gas into the first engines of light. Darkness filled space before the first stars switched on. After the ancient background light was released, the universe entered an era sometimes called the Cosmic Dark Ages. There was matter everywhere, but nothing yet shone like a star. Space was transparent, but it was not lit by galaxies or suns. Hydrogen gas drifted through the expanding cosmos, and faint density differences slowly deepened under gravity. In that long interval, the universe was becoming ready. Invisible regions of gas were gathering into larger clouds, building pressure in their centers, and moving toward the moment when nuclear fusion could begin. Then, at last, the first true stellar fires appeared. That transition was one of the great turning points in cosmic history. Light returned, not as leftover radiation from the beginning, but as fresh energy made inside stars. The first starlight began altering the gas around it, breaking atoms apart and changing the universe's chemistry. Darkness was not empty. It was the pause before cosmic structure began to shine. The first stars may have been gigantic and short-lived. The earliest stars formed from almost pure hydrogen and helium, with almost none of the heavier elements that help gas cool today. Because cooling was less efficient, those first clouds may have collapsed into very massive stars. Some could have been far larger than most stars now forming in the modern universe. Their lives would have been fierce and brief. Massive stars burn through fuel quickly because their cores are under enormous pressure and run nuclear reactions at a furious pace. A star like the Sun can shine for billions of years, but the first giants may have lasted only a few million years. In that short time, they changed everything around them. Their radiation transformed nearby gas, and their deaths may have produced the first waves of heavier elements. We have not directly observed a pristine first star yet, but their fingerprints may be hidden in ancient gas clouds and the oldest surviving stars. Ancient stars changed the universe by creating heavier elements. At first, the cosmos had only a very small chemical vocabulary. Hydrogen and helium dominated almost completely, with only traces of a few light elements. Stars expanded that vocabulary. In their cores, pressure and heat forced nuclei together, building new elements from simpler ones. This process did not happen all at once. Each generation of stars added something to the mixture. Some stars made carbon and nitrogen during long phases of internal burning. More massive ones created elements such as silicon and sulfur before they died. Once these materials were released, later stars and planets formed from richer clouds. This is why astronomers call elements heavier than helium metals, even when they are not metals in everyday speech. To them, those ingredients measure how much stellar history has gone before. The universe became chemically interesting through the lives and deaths of stars. Without those early forges, space would have remained too simple for rocky worlds to exist. Supernova seeded space with the ingredients for rocky worlds. A massive star's death can be one of the most productive events in nature. When its core collapses, the outer layers blast outward at tremendous speed, carrying newly made elements into surrounding space. This explosion does not merely destroy. It enriches the galaxy. Oxygen, magnesium, silicon, calcium, and many other ingredients can be hurled into interstellar clouds, where they mix with older gas. Later, those clouds may collapse into new star systems. The dust grains that help build planets often contain material that passed through these violent endings. A rocky world is therefore not just assembled from calm cosmic leftovers. It can be made from the scattered remains of stars that died catastrophically. Earth's crust, mountains and minerals all belong to a chain that includes such explosions. Supernovae are frightening in scale, yet they are also creative. They turn stellar interiors into future geology, making solid planets possible across the galaxy. Gold was likely forged in colliding neutron stars. For a long time, scientists knew that precious heavy elements needed extreme conditions, but the exact cosmic birthplace of many of them remained uncertain. Then, astronomers observed the aftermath of a neutron star merger, and the evidence became spectacular. When two of these ultra-dense remnants spiral together, they tear matter loose under conditions unlike almost anything else in the universe. In that debris, atomic nuclei can capture neutrons rapidly, building very heavy elements before the material settles into stability. This process can create gold, platinum, and other rare substances. The event also produces a glow called a kilonova, which carries signatures of freshly made heavy elements. Think of what that means. A ring, a circuit, or a tiny fleck of gold may contain atoms born in the collision of dead stars. Something valued for its beauty on Earth may have begun in one of the most violent mergers the cosmos can produce. Carbon atoms were cooked inside aging red giant stars. Carbon is central to life because it bonds in flexible, complex ways. But it did not exist in abundance at the beginning. One important source is the interior of aging stars that have swollen into red giants. After a star uses much of its hydrogen fuel, its core changes and helium can begin fusing into carbon through a delicate sequence of reactions. This process requires a remarkable balance of nuclear physics. 3 helium nuclei must come together in conditions of intense heat and density, and the result is carbon. Later, the star can dredge this material upward and release it through winds that carry enriched gas into space. Some of that carbon becomes dust. Some joins clouds that form new stars. Some eventually becomes planets, atmospheres, oceans, and organisms. The element that makes long chains in biology was prepared inside stars that were nearing the ends of their lives. Living chemistry has an ancient stellar kitchen. Oxygen became common because massive stars lived fast and died. Oxygen is one of the great elements of the cosmos. It fills rocks, water, atmospheres, and living tissue, yet its abundance depends strongly on massive stars. These stars run hotter and faster than smaller ones. Deep in their interiors, nuclear reactions build oxygen from lighter elements during advanced stages of stellar burning. Because massive stars have short lives, they return their products to space quickly on cosmic timescales. Their winds and explosions enrich nearby gas with oxygen long before smaller stars finish their slower evolution. This matters enormously for planets. Oxygen bonds readily with silicon, magnesium, iron, and hydrogen, helping create minerals and water. When astronomers study oxygen in distant galaxies, they are also studying the pace of stellar birth and death. The oxygen in a breath did not come directly from those ancient explosions in its molecular form, but the atoms themselves were made by stars that burned brilliantly and ended violently. Iron marks the final fuel of many massive stars. A massive star survives by balancing gravity against energy released from nuclear fusion. For much of its life, fusion provides outward pressure, keeping the star from collapsing under its own weight. As it ages, it burns through different fuels in layers, creating heavier elements in its core. But iron is different. Fusing iron does not release useful energy in the way lighter elements do. Instead of helping support the star, iron signals that the core has reached a dead end. When enough iron builds up, the pressure support can fail. Gravity wins, and the core collapses with astonishing speed. That collapse can trigger a supernova, sending the outer layers outward, while the inner core becomes a compact remnant. Iron is familiar to us in tools, buildings, blood, and planetary cores, but in massive stars, it carries a dramatic meaning. It is the ash of fusion, the point where one kind of stellar life can no longer continue. A supernova can outshine its entire galaxy for weeks. When a star explodes at the end of its life, the release of energy can be so intense that a single point of light rivals billions of stars. For a brief period, the dying star may become brighter than the galaxy that contains it. Astronomers can see such events across immense distances, which makes them powerful markers in the history of the universe. Some supernovae also follow predictable brightness patterns, allowing scientists to measure cosmic distances and study the expansion of space. Up close, such an explosion would be devastating. From far away, it is a brilliant signal that something profound has happened. The blast sends shock waves through nearby gas, sometimes compressing clouds and influencing later star formation. It also leaves behind expanding remnants that glow for thousands of years. A supernova is not only a final flare. It is an announcement, a chemical delivery system, and a cosmic beacon all at once. Neutron stars are city-sized remnants with star-sized mass. After some massive stars explode, their cores collapse into objects so dense that ordinary atoms cannot survive. Protons and electrons are crushed together, forming matter dominated by neutrons. The result can contain more mass than the Sun packed into a sphere only about the width of a large city. This density is almost impossible to picture. A tiny amount of neutron star material would weigh more than mountains if it could exist on Earth. Gravity at the surface is extreme, and the crust may be harder than any known material. These objects are not simply dead cinders. They can spin rapidly, hold intense magnetic fields and release powerful radiation. Their interiors may contain exotic states of matter that laboratories cannot reproduce. A neutron star is a natural experiment created by gravity. It takes the remains of a stellar core and compresses them until matter enters a realm far beyond everyday experience. Pulsars flash with astonishing regularity as they spin. Some neutron stars reveal themselves as cosmic lighthouses. They send beams of radiation from their magnetic poles, and if those beams sweep across Earth, our telescopes detect pulses. The timing can be extraordinarily precise. Some pulsars rotate many times each second, while others tick more slowly, but their signals can be stable enough to rival fine clocks. This regularity helped astronomers realize they were not seeing random flickers. They were watching compact remnants turning in space. Pulsars have become tools for studying gravity, dense matter, and the space between stars. Their pulses can reveal whether they are orbiting another object, moving through gas, or slowly losing rotational energy. Some scientists even use networks of pulsars to search for very long wavelength gravitational waves. What began as mysterious repeating signals became one of astronomy's greatest discoveries. A collapsed star can announce its presence not with steady light, but with a rhythm sharp enough to measure the cosmos. Magnetars have the strongest magnetic fields ever observed. Among neutron stars, magnetars are the extreme specialists. Their magnetic fields can be 1,000 trillion times stronger than Earth's, and that strength changes how matter behaves around them. The field can stress the star's crust until it cracks, releasing enormous bursts of high-energy radiation. Some flares from magnetars are so powerful that they can affect detectors and satellites from across the galaxy. The object itself may be only city-sized, but its magnetic influence is vast and violent. Scientists think magnetars are born when certain stellar cores collapse under conditions that amplify magnetic fields to incredible levels. They do not shine steadily like ordinary stars. Instead, they can erupt unpredictably, as if the star's own magnetism is twisting and snapping. Magnetars show that gravity is not the only force capable of producing cosmic extremes. Magnetism, when packed into a collapsed star, becomes one of the most intense powers known in nature. Some stars die quietly and become white dwarfs. Not every star ends with a dramatic explosion. Stars more like the Sun follow a slower path. After swelling into a red giant, such a star sheds its outer layers into space, leaving behind a hot, compact core. That core becomes a white dwarf. It no longer generates energy through normal fusion, but it remains intensely hot from its previous life. Over time, it cools gradually, shining with stored heat. The material inside is packed tightly by gravity, but it is supported by quantum pressure rather than ordinary gas pressure. A white dwarf can be roughly Earth-sized while holding a mass comparable to the Sun. Around it, the expelled outer layers may glow as a planetary nebula, forming delicate shells of gas. This ending is quiet only compared with a supernova. It is still a profound transformation. A star that once warmed planets can become a dense ember, fading with extraordinary patience. White dwarfs can burn for longer than the universe's current age. A white dwarf does not burn fuel like a living star, but it can glow for an almost unimaginable length of time. Its light comes from heat stored in its dense interior. Because it is small and compact, it loses that heat slowly. The universe is not old enough for any white dwarf to have cooled completely into the theoretical state called a black dwarf. Everyone we observe is still somewhere along that immense cooling path. This makes white dwarfs useful cosmic clocks. By studying their temperatures and brightness, astronomers can estimate the ages of star populations. In the distant future, After many brighter stars have died, white dwarfs may become some of the last faint lights in aging galaxies. They are reminders that stellar death is not always quick. Sometimes it is a cooling process so slow that the universe has not yet had enough time to finish even the first examples. Brown dwarfs are failed stars that never truly ignited. Between the smallest stars and the largest planets lies a strange class of object. Brown dwarfs form from collapsing gas clouds, as stars do, but they do not gather enough mass to sustain long-term hydrogen fusion in their cores. Some can briefly fuse a heavier form of hydrogen called deuterium, but they never become stable stars like the Sun. They glow faintly with leftover heat, cooling over time until they become harder to detect. Their atmospheres can contain clouds, storms, and molecules more familiar from giant planets than stars. Yet they form like stars, often alone in space or in wide orbits around other stars. Brown dwarfs blur categories that once seemed simple. They are not planets in the usual sense, and they are not full stars either. They occupy the cosmic borderland between ignition and failure. In them, nature shows that star formation can almost succeed, then settle into a long, dim afterlife. Red dwarf stars may shine for trillions of years. The smallest true stars are also the most enduring. Red dwarfs burn their hydrogen fuel slowly and efficiently with modest temperatures and faint light. Because they use their fuel at such a careful pace, they can last far longer than stars like the Sun. Some may remain active for trillions of years, which is far beyond the current age of the universe. This means no red dwarf has yet lived out its full natural lifespan. They are common too, making up a large share of the galaxy's stellar population. Around them, planets may be abundant, although conditions can be complicated by stellar flares and close orbits. In the far future, when larger stars have vanished, red dwarfs may still be shining. They could become the long-lasting hearths of an older cosmos. Their quiet persistence changes our sense of time. The universe we know is still young compared with the lives of its smallest stars. The Sun formed from recycled material left by older stars. Our star did not appear from untouched cosmic gas. It formed from a cloud already enriched by earlier generations of stellar life. That cloud contained hydrogen and helium, but also heavier elements made in stars that lived and died before the Sun existed. These ingredients became part of the newborn solar system. The Sun inherited them, and so did the planets, moons, asteroids, and comets. Scientists can read this history in the chemical composition of meteorites and in the abundance of elements found in the Sun itself. The solar system is therefore not a first chapter. It is a later paragraph in a much older galactic story. Before the Sun shone, other stars had already forged silicon, iron, carbon, oxygen, and many other elements. Their released material drifted through interstellar space until gravity gathered it again. Our daylight comes from a star born out of cosmic recycling, carrying the memory of vanished suns. Our solar system was born inside a spinning disk. The Sun formed from a collapsing cloud of gas and dust. As the cloud shrank under gravity, its rotation became more important, and material flattened into a disk around the young star. This disk was the birthplace of the planets. Close to the Sun, temperatures were high, so metals and rocky minerals could condense while lighter ices were less stable. Farther out, colder conditions allowed more volatile materials to freeze and gather. Within the disk, dust grains collided, clumped, broke apart, and clumped again. Over time, larger bodies formed and swept up more material. The architecture of the solar system still carries traces of that original disk. The planets orbit in roughly the same plane because they formed within that flattened structure. It is a beautiful example of order emerging from collapse. A drifting cloud became a rotating nursery, and from that nursery came the Sun's family of worlds. Planets grew from dust grains sticking together in darkness. The first steps of planet formation were astonishingly small. Tiny particles in the young solar disk met one another, sometimes bouncing away and sometimes sticking through weak forces. These dust grains became larger clumps. The clumps became pebbles, then boulders, then planetesimals large enough for gravity to matter strongly. Once gravity took over, growth could accelerate. Larger bodies attracted more material, while collisions became powerful enough to reshape or even melt young worlds. This process was messy, not smooth. Many early objects were destroyed. Others merged. Some were thrown into new orbits or lost completely. Yet from this restless environment, planets emerged. It is remarkable to think that Earth began through countless tiny acts of assembly in a dark disk around a young star. There was no blueprint, no single moment when dust became destiny. There was accumulation, impact, heating, and survival. A planet began as grains too small to notice. Jupiter may have shaped the architecture of our solar system. The largest planet is not merely another world orbiting the Sun. Its gravity has influenced the entire system. During the early stages of planet formation, Jupiter may have migrated through the disk, disturbing smaller bodies and helping determine where material could gather. Its presence affected the asteroid belt, influenced the growth of the inner planets, and helped scatter icy objects across distant regions. Some models suggest that Jupiter and Saturn together prevented the inner solar system from becoming packed with larger rocky worlds. Jupiter also continues to shape orbits today. Its gravitational pull can redirect comets and asteroids, sometimes sending them inward and sometimes ejecting them away from the Sun. It acts as both disruptor and shield, depending on the object and its path. Without Jupiter, the solar system might have developed very differently. Earth's history is not only a story of our planet, it is also shaped by the giant neighbor that dominates the outer system. Earth formed after countless collisions between young, rocky bodies. Our planet was not assembled gently. In the young inner solar system, rocky objects orbited the Sun in crowded paths. They collided again and again, merging into larger bodies through impacts that released enormous heat. Early Earth was likely molten in places, with heavy materials sinking inward and lighter materials rising toward the surface. Iron gathered into the core, while silicate rock formed the mantle and crust. Each collision changed the growing planet's mass, chemistry, spin, and heat. Some impacts added material, others blasted debris into space. The process took tens of millions of years and ended with a world still hot, restless, and changing. This origin matters because it explains why Earth has layers, why it retained internal heat, and why its early surface was so unlike the familiar planet we know. The calm ground beneath us is the cooled result of an ancient construction zone built by impact. The Moon likely began after a Mars-sized impact. One of the most dramatic events in Earth's history may have created its companion. The leading idea is that a large body, often called Theia, struck the young Earth during the final stages of planet formation. The impact was so powerful that it threw enormous amounts of material into orbit. This debris formed a disk around Earth, and from that disk, the Moon gathered together. The theory helps explain important features of the Earth-Moon system, including the Moon's relatively large size and the similarities in some chemical signatures between lunar rocks and Earth's mantle. The collision would have transformed our planet, adding heat and changing its rotation. The Moon then influenced Earth's future by stabilizing its axial tilt and driving tides. A catastrophic impact became part of the reason our world developed the rhythms it has today. The bright disk in the night sky may be the lasting child of a violent beginning. Earth's water may have arrived from asteroids and ancient minerals. The origin of Earth's water is more complex than a single delivery event. Some water may have been present in the materials that built the planet, locked into minerals or carried by hydrated rocky bodies. More may have arrived later through impacts from asteroids rich in water-bearing compounds. Comets were once popular candidates, but many have water with isotopic signatures that do not match Earth as closely as some asteroid families do. The answer may involve several sources, blended over time. Water could have survived inside minerals during Earth's formation, been released by volcanic activity, and been supplemented by later impacts. This matters because water shaped the surface, atmosphere, climate, and eventual habitability of the planet. Every ocean may represent a combined inheritance from deep planetary chemistry and small bodies that crossed Earth's path. The water in a glass is not just local. It belongs to a long story of minerals, impacts, and planetary transformation. Meteorites preserve chemistry from before the planets were born. A meteorite can look like an ordinary stone, but some are older than Earth itself. Certain meteorites contain primitive material that formed in the early solar disk before planets finished assembling. Inside them are tiny mineral grains, metal flecks, and chemical patterns that record conditions from the solar system's birth. Some even contain pre-solar grains, which formed around other stars before the Sun existed. These grains survived the journey into the cloud that made our solar system and became trapped in small bodies that avoided complete melting. When such meteorites fall to Earth, scientists receive samples from a time no spacecraft could visit directly. By studying isotopes and minerals, researchers reconstruct temperatures, timelines, and processes from the earliest chapters of planetary formation. A meteorite is not just debris. It is a physical archive. Held in the hand, it may contain matter older than the Sun, and clues from before Earth had a name. Comets carry frozen records of the solar system's youth. Far from the Sun, icy bodies preserved materials that were too volatile to survive in hotter regions. Comets are among these ancient keepers. They contain mixtures of ice, dust, organic molecules, and rocky grains, often stored for billions of years in cold outer reservoirs. When a comet travels inward, sunlight warms its surface, and gas escapes into space, carrying dust with it. This creates the glowing coma and tail that make comets so striking from Earth. But their beauty is only part of their importance. Their composition gives scientists clues about the early solar disk and the conditions where icy objects formed. Space missions have visited comets, tasted their gases, and photographed their dark surfaces in remarkable detail. These objects are not dirty snowballs in any simple sense. They are layered remnants from the Sun's youth, preserving fragile chemistry that helps reveal how planets and smaller bodies formed. The asteroid belt never became a planet. Between Mars and Jupiter lies a broad region filled with rocky bodies, but it is not the wreckage of one exploded world. The total mass of the asteroid belt is far too small for that story, and its objects show varied compositions rather than pieces of a single planet. Instead, the belt is a leftover zone where planet formation never fully succeeded. Jupiter's gravity played a major role, stirring up orbits and preventing material from gathering into one stable planet. Collisions continued, but they often broke bodies apart rather than building them into something larger. Today, the belt contains asteroids of many sizes, from dwarf planet series to small fragments and rubble piles. It is a museum of incomplete assembly. Some asteroids are metallic, others rocky, and others rich in carbon compounds. Together, they preserve pieces of the early solar system that escaped being absorbed into planets. Their unfinished nature makes them scientifically priceless. Neptune's gravity helps sculpt the distant Kuiper belt. Beyond Neptune lies a vast region of icy bodies orbiting in the cold outskirts of the solar system. Their paths are not random. Neptune's gravity has shaped many of them over billions of years. Some objects are locked into orbital resonances, which means they complete their paths around the Sun in patterns tied to Neptune's orbit. Pluto is a famous example of this kind of relationship. These resonances can protect objects from close encounters while still revealing Neptune's influence. The planet may also have migrated outward early in solar system history, disturbing icy bodies and scattering many into new orbits. This helped create the structure we see today. The Kuiper belt is therefore not just a distant storage zone. It is a region marked by gravitational history. By studying the orbits of its objects, scientists can reconstruct how the giant planets moved long ago. Neptune is far away, but its reach is written across the frozen edge. Pluto belongs to a vast family of icy worlds. For much of the 20th century, Pluto seemed like a strange little planet on its own. Then astronomers began discovering many other icy bodies beyond Neptune, and Pluto's true context became clearer. It is one member of the Kuiper belt, a region filled with frozen worlds, fragments, and dwarf planets. Some of these objects have moons. Some have reddish surfaces shaped by complex chemistry. Some follow tilted or elongated orbits that hint at a turbulent early history. Pluto remains remarkable, especially after spacecraft revealed mountains of water ice, plains of nitrogen ice, and signs of active surface processes. But it is no longer alone in our imagination. It belongs to a population that changed how scientists define the outer solar system. Its reclassification was not a demotion in wonder. It was a promotion into a richer story. Pluto became the gateway to a whole frontier of small worlds beyond the classical planets. The Oort cloud may surround the Sun with ancient comets. Far beyond the planets and the Kuiper belt, astronomers think the solar system is enclosed by a vast, distant reservoir of icy bodies. This region has not been observed directly because its objects are too small, too cold, and too spread out. Its existence is inferred from long-period comets that fall inward from all directions, as if they began in a great spherical shell around the Sun. These comets may have formed closer to the giant planets before gravitational encounters scattered them far outward. There, they drift on enormous orbits that can take millions of years to complete. Passing stars and galactic tides may occasionally disturb them, sending a few toward the inner solar system. If this cloud exists as expected, it marks the Sun's most distant family of objects. It is less like a boundary wall and more like a faint outer memory, holding icy remnants from the solar system's earliest days. Rogue planets wander the galaxy without any parent star. Some worlds do not rise beneath any sun. They drift alone through interstellar space, unlit by day and untouched by seasons in the usual sense. These planets may have formed around stars and later been thrown out by gravitational chaos, especially during the crowded early stages of planetary systems. Others might have formed directly from collapsing clouds of gas, more like tiny failed stars than ordinary planets. Without a nearby star, their surfaces would be bitterly cold. But that does not make them simple. A thick atmosphere could trap internal heat. A layer of ice could hide a liquid ocean warmed from below by radioactive decay or tidal history. Some may even carry moons into darkness, forming miniature systems that travel together. Astronomers detect them through gravitational microlensing when a wandering world briefly bends the light of a background star. These lonely planets remind us that a world does not need a sunrise to have a story. Some exoplanets orbit two suns and see double sunsets. For generations, twin star worlds belonged mostly to science fiction. Then astronomers began finding real planets moving around binary stars, proving that nature can build stable worlds in systems once thought too chaotic. In some cases, a planet circles both stars at once, tracing a wide path around their shared center of mass. From its surface, if it has one, the sky would change in unfamiliar ways. Days could vary as the stars eclipse one another or shift positions. Shadows might not behave as they do on Earth. Seasons could depend not only on the planet's tilt and orbit, but on the dance of the suns themselves. These worlds are difficult to find because the light from two stars complicates the signal, yet several have been confirmed. Their existence shows that planet formation is more adaptable than we once imagined. Even in a system with two blazing centers, gravity can still make room for worlds. Hot Jupiters circle their stars in only a few days. The first planets found around sun-like stars shocked astronomers because they were nothing like our solar system's giants. Instead of orbiting far from their stars, some Jupiter-sized worlds were racing extremely close to them. These hot Jupiters can complete an entire year in just a few Earth days. Their upper atmospheres are blasted by radiation, heated to extreme temperatures, and sometimes swollen into enormous envelopes. Many are tidally locked, with one hemisphere facing constant starlight, while the other remains in permanent night. Winds may race between the two sides, trying to redistribute heat across a planet larger than any world in our inner solar system. The great mystery is how they got there. Giant planets are thought to form farther out, where icy materials are available, so hot Jupiters likely migrated inward or were pushed by gravitational interactions. They forced scientists to rethink planetary systems, because the universe clearly does not arrange worlds the way ours does. Lava worlds may have oceans made of molten rock. Some planets orbit so close to their stars that their surfaces may not be solid in any familiar way. On the day side of these worlds, temperatures can rise high enough to melt rock. Instead of water seas, there may be glowing oceans of liquid silicate with waves made from minerals that would form cliffs on Earth. The atmosphere, if one exists, could contain vaporized rock, sodium, and other unusual gases pulled from the molten surface. Winds might carry this material toward cooler regions, where it could condense and fall as mineral rain. The night side may be cooler, perhaps crusted over in hardened lava, creating a stark contrast between furnace and darkness. These worlds are laboratories for extreme geology. They show what happens when a rocky planet is held too close to stellar fire. Earth's pearly surface was once molten after huge impacts, but on lava worlds, that ancient nightmare can become a permanent climate. Some planets could rain glass sideways in brutal winds. One famous blue exoplanet has weather so violent that the word rain almost feels too gentle. Its color may come from tiny silicate particles high in the atmosphere, the same basic ingredients found in glass. The planet orbits close to its star, so its air is heated to fierce temperatures, while powerful winds race around the globe at extraordinary speeds. Under those conditions, silicate droplets may form and fall, not downward in a calm shower, but sideways through a roaring atmosphere. From far away, the world looks beautifully blue, almost inviting at first glance. But that color hides a place where skies are filled with mineral haze and storm systems beyond anything on Earth. It is a reminder that appearances can deceive in astronomy. A familiar color does not promise familiar conditions. Across the galaxy, nature has made worlds where weather is not water cycling through air, but molten minerals driven through alien skies. Ocean worlds may hide global seas beneath icy crusts. Some of the most promising places to search for life may not look habitable at first. They may be frozen on the outside, with surfaces of hard ice, far from the warmth of any star. Yet beneath that shell, a deep liquid ocean can survive if internal heat keeps the water from freezing completely. In our own solar system, moons such as Europa and Enceladus have made this idea feel very real. Their oceans may be warmed by tidal flexing, as gravity kneads their interiors during orbit. Cracks, plumes, and surface patterns hint at hidden movement below. Around other stars, similar worlds may be common. An icy crust can act like a shield, protecting water from radiation and preserving a stable environment beneath. If chemistry, energy, and liquid water meet there, biology becomes an open question. These worlds suggest that life might not always need sunlight on the surface. It might begin in covered oceans. Diamond-rich planets could form around carbon-heavy stars. Not every planetary system begins with the same chemical balance. Around stars with more carbon relative to oxygen, the solid material available for building planets could be very different from the mix that made Earth. Instead of silicate rocks dominating, carbon compounds might become far more important. Under extreme pressure inside a large rocky planet, some of that carbon could be transformed into diamond. Such a world would not look like a sparkling jewel in a display case. Its surface might be dark, hot, and crushed by heavy geology, while deep inside, vast layers of crystalline carbon could exist beyond reach. These planets are still candidates and possibilities rather than familiar places, but the idea is scientifically serious because planet chemistry depends on the ingredients present at birth. Earth is rich in oxygen bonded to rock. Elsewhere, a planet's interior might be built around carbon's strange versatility, turning planetary geology into something profoundly unfamiliar. Super-Earths may be rocky worlds larger than our planet. Between Earth and Neptune lies a planetary size range that our solar system strangely lacks. Astronomers call many of these worlds super-Earths, though the name can be misleading. It does not mean they are better than Earth, or necessarily habitable. It means they are larger than our planet, but smaller than icy giants like Neptune. Some may be rocky. Others may hold thick atmospheres, deep oceans, or dense envelopes of gas. Their gravity could be much stronger than ours, affecting mountains, atmospheres, and volcanic activity. Because they are common around other stars, their absence here is one of the quiet puzzles of planetary science. Studying them helps scientists understand how planets grow, how atmospheres are kept or lost, and how size changes the fate of a world. Somewhere among them may be planets with stable climates, active interiors, and long histories. The galaxy may contain many Earth-like ingredients arranged on a larger scale. Many Neptunes are common, yet absent from our solar system. One of the biggest surprises from exoplanet surveys is the abundance of worlds larger than Earth, but smaller than Neptune. Many of these are called mini-Neptunes. They may have rocky or icy cores wrapped in thick atmospheres of hydrogen and helium, perhaps with clouds and chemistry unlike anything nearby. Our solar system has rocky inner planets and large outer giants, but nothing in this middle category. That absence makes these worlds especially important. They may represent a common outcome of planet formation that our system somehow avoided or lost during its early history. Some mini-Neptunes orbit close to their stars, where radiation can slowly strip away their atmospheres. Others may keep their envelopes for billions of years. They are not easy to picture because no local example waits for spacecraft comparison. Each discovery reminds us that our solar system is not the template for all others. It is only one arrangement among many. Astronomers can study alien atmospheres by watching starlight dim. when a planet passes in front of its star, it blocks a small portion of the star's light. That tiny dip can reveal the planet's size and orbit. But there is an even more delicate clue hidden in the starlight. Some light passes through the planet's atmosphere before reaching us, and gases in that atmosphere absorb specific colors. By splitting the light into a spectrum, astronomers can search for fingerprints of molecules such as water vapor, carbon dioxide, methane, or sodium. This method turns a distant world into a shadow with chemistry. The planet itself may be too far away to image clearly, yet its air can leave readable marks across interstellar distance. The measurements are difficult because stars are bright and planets are small, but modern telescopes are making them increasingly powerful. Through these faint changes in light, scientists are beginning to ask what alien skies are made of, and whether any might hint at habitability. The Milky Way contains hundreds of billions of stars. Our galaxy is so large that ordinary numbers begin to lose their meaning. The Sun is only one star among a vast population, spread through a disk, a central bulge, and a surrounding halo. Some stars are bright blue and short-lived. Others are small red stars that may last for immense stretches of time. Many are hidden from our eyes by dust, distance, or faintness. From Earth, the Milky Way appears as a pale band across dark skies because we are looking through the crowded plane of the galaxy from within it. We cannot step outside to take a full photograph. So astronomers build its map from star counts, gas motions, infrared observations, and radio signals. The result is a grand spiral system that contains our entire known home. Every constellation we see belongs to this local stellar city. The night sky is not scattered at random. It is our view from inside a galaxy. Our galaxy is surrounded by a halo of dark matter. The visible Milky Way is only part of the structure we live inside. Around the stars and gas is a much larger halo of unseen mass, inferred from the way gravity behaves. Stars in the outer galaxy move too quickly to be explained by visible matter alone. Dwarf galaxies orbiting the Milky Way also reveal the pull of something more extended. This dark matter halo may reach far beyond the bright disk, forming an enormous gravitational envelope. It does not glow, block light, or form ordinary atoms, at least as far as current evidence shows. Yet it shapes how the galaxy holds together and how it grew over time. Without this hidden framework, the Milky Way's structure would be difficult to explain. We live inside a luminous disk embedded in a far larger invisible architecture. The stars are the part we can admire, but the unseen halo may provide much of the galaxy's gravitational foundation. The Milky Way's center holds a supermassive black hole. At the heart of our galaxy lies an object so compact and massive that stars whip around it at extraordinary speeds. Astronomers tracked those stellar orbits for years and found that they circle something invisible, containing millions of solar masses in a very small region. This object is called Sagittarius, a star. It is far less active than the brilliant black holes that power quasars, but it is still the gravitational anchor of the galactic center. Around it lies a crowded environment of stars, gas clouds, magnetic fields, and energetic radiation. Occasionally, material falling nearby produces flares, giving scientists a glimpse of the physics close to the event horizon. The discovery transformed the idea of our galaxy. The Milky Way is not only a spiral of stars. It is organized around a dark central engine. Deep behind the dust of the galactic core, a black hole sits at the center of our stellar home. Sagittarius A star weighs millions of times more than the Sun. The mass of our galaxy's central black hole is known not by seeing its surface, because it has none, but by watching what moves around it. Stars near the galactic center follow tight, fast orbits, especially one famous star that loops close enough to reveal the central object's gravity with remarkable precision. From these motions, astronomers calculate a mass of about 4 million suns packed into a region smaller than our solar system. That is enormous by human standards, yet modest compared with some supermassive black holes in other galaxies, which can weigh billions of suns. Sagittarius A star is therefore both extreme and strangely restrained. It is powerful enough to dominate the very center of the Milky Way, but not currently feeding at the rate needed to blaze as a quasar. Its relative calm lets us study a supermassive black hole in our own cosmic neighborhood, close enough for details that distant galaxies cannot reveal. Stars orbit the galactic center at breathtaking speeds. Near the Milky Way's core, gravity rules with stunning force. Stars close to the central black hole move along paths that would seem impossible in our calmer neighborhood. Some reach thousands of kilometers per second as they swing through the inner region. Their orbits are not only fast, they are scientific evidence. By tracking their positions over years, astronomers proved that a huge amount of mass must be concentrated in a tiny volume at the galactic center. These stars act like test particles, tracing the invisible gravitational field around them. One of them passes close enough to test predictions from general relativity, because its path shifts slightly as space-time curves near the black hole. Imagine a star as a probe, not built by humans, but placed by nature in the perfect orbit to reveal hidden mass. Around the center of the Milky Way, stars become messengers, carrying information through their motion. Our solar system takes 1 galactic year to circle home. Earth orbits the Sun once each year, but the Sun is also moving around the center of the Milky Way. This larger journey takes roughly 225 million Earth years. That span is sometimes called a galactic year. Since the solar system formed, it has completed only about 20 such circuits. The last time we were in a similar position around the galaxy, the continents, climates, and living world of Earth were dramatically different. The path is not a perfect, simple circle. The Sun moves with the rotating disk while also bobbing slightly above and below the galactic plane. During this journey, it passes through changing neighborhoods of gas, dust, and stars. Human history is so brief that this motion feels invisible, yet it never stops. While we measure days by sunrise, our entire planetary system is also traveling through the Milky Way on a timescale that dwarfs biology and civilization. The Milky Way has swallowed smaller galaxies before. Our galaxy carries evidence of ancient meals. In the halo around the Milky Way, astronomers find stars moving in streams and groups that do not match the motion of the main disk. Their chemistry and orbits suggest they once belonged to smaller galaxies that were pulled apart by gravity. One major past merger, identified through stellar motions, seems to have added a large population of stars to the halo billions of years ago. These events help build the Milky Way into the galaxy we know. The process is not like a monster gulping down stars one by one. It is a slow gravitational unraveling, where a smaller galaxy loses its shape and becomes part of a larger system. This history means the Milky Way is partly assembled from outsiders. Some stars overhead may not have been born in our galaxy at all. They may be immigrants from vanished systems, now woven into our sky. Stellar streams reveal galaxies that our Milky Way consumed. When a dwarf galaxy or star cluster falls into the Milky Way, it can be stretched by tidal forces into a long ribbon of stars. These stellar streams may wrap around the galaxy like faint trails, preserving the orbit of the object that created them. They are difficult to detect because their stars are spread thinly across the sky, but modern surveys have revealed many of them. Each stream is a clue, to a lost structure. By mapping its path, scientists can infer the gravitational shape of the Milky Way, including the distribution of dark matter. Streams are therefore both fossils and measuring tools. They show where smaller systems were torn apart, and they help reveal the invisible mass through which they move. The sky may look fixed and serene, but hidden within it are the remains of gravitational encounters. Stellar streams are the handwriting of galactic history, drawn in stars. Andromeda is moving toward the Milky Way right now. Most distant galaxies are carried away from us by cosmic expansion, but nearby galaxies can be dominated by local gravity. Andromeda, the largest spiral galaxy in our local group, is one of them. It is approaching the Milky Way across intergalactic space. To our eyes, it appears as a faint smudge under dark skies, yet it contains roughly 1 trillion stars and spans a vast region. Measurements of its motion show that the two great galaxies are gravitationally bound and slowly drawing closer. This approach is not a sudden danger. The timescale is measured in billions of years. Still, it is extraordinary to know that the night sky contains another spiral system that is not simply passing by. It is part of our long future. While human lifetimes are brief, galaxies move according to deeper clocks. Andromeda's faint glow is both a neighboring island of stars and the beginning of an eventual transformation. The Milky Way and Andromeda will someday merge. In the distant future, the two largest galaxies of the local group are expected to combine. The event will unfold slowly, over billions of years, as gravity pulls them through repeated close passages. Their spiral forms will be distorted, stretched, and eventually blended into a new galaxy. Despite the enormous scale, individual stars are unlikely to collide because the spaces between them are so large. The real drama will happen through gravity, which will rearrange stellar orbits and stir vast clouds of gas. New star formation may occur where gas is compressed. The Sun, if it still exists in its late stages, could be sent into a new orbit far from its current path. This future merger reminds us that galaxies are not permanent sculptures. They are dynamic systems, shaped by encounters. The Milky Way's familiar form is temporary. One day, our home galaxy and its great neighbor may become a single larger system. Galaxy collisions rarely make individual stars crash together. It sounds impossible at first. Two galaxies can pass through each other, each containing hundreds of billions of stars, and almost none of those stars will physically collide. The reason is scale. Stars are large, but the distances between them are far larger. If stars were grains of sand, the gaps between them would be enormous. During a galactic encounter, gravity changes everything. Orbits shift. Spiral arms stretch. Gas clouds collide and compress. Star formation can flare up in bright regions. But the stars themselves mostly glide past one another through the vast emptiness. This makes galaxy collisions both violent and strangely spacious. The shapes of whole galaxies can be transformed while their individual stars survive direct impact. To a planet around one of those stars, the sky might change over immense time, growing richer with new patterns of light. The collision is real, but it is a gravitational dance more than a crowded crash. Elliptical galaxies can contain trillions of old stars. Not all galaxies have graceful spiral arms. Some are vast, smooth and rounded, with stars moving in many different directions rather than in a thin rotating disk. These are elliptical galaxies, and the largest of them are cosmic giants. They often contain older stars and relatively little cold gas compared with active spiral galaxies. Because new star formation needs cold gas, many ellipticals glow with the warmer colors of aging stellar populations, rather than the blue light of newborn massive stars. Some likely formed through mergers, where spiral galaxies lost their ordered disks and settled into broader, puffier structures. At the centers of large ellipticals, supermassive black holes can be enormous. These galaxies may sit in the hearts of galaxy clusters, surrounded by swarms of smaller companions. An elliptical galaxy may look simple at first glance, like a soft ball of light, but it can contain the blended history of many galaxies that came before it. Spiral galaxies turn slowly around hidden gravitational structures. A spiral galaxy is one of the most recognizable shapes in the universe, but its beauty depends on forces we cannot fully see. The bright arms contain stars, gas, and dust, yet the motion of the galaxy suggests the presence of a much larger dark matter halo. Without that unseen mass, outer stars would not move the way observations show. The spiral pattern itself is not like fixed material arms spinning as solid structures. Instead, it can behave more like a wave of density passing through the disk, compressing gas and helping trigger star formation. Young, bright stars then outline parts of the pattern, making the arms shine. This means a spiral galaxy is both a visible design and a hidden gravitational system. What we admire in telescope images is the luminous trace of deeper dynamics. The galaxy turns, but not as a simple wheel. It is a vast rotating disk, guided by visible matter and invisible mass together. Dwarf galaxies help build larger galaxies over cosmic time. The universe grows from the small as well as the grand. Dwarf galaxies contain far fewer stars than giants like the Milky Way, but they play an important role in cosmic evolution. Many formed early, in small dark matter halos, and some preserved ancient stars that carry clues from the young universe. Over time, larger galaxies captured and absorbed many of these smaller systems. Their stars were scattered into halos. Their gas could feed new star formation. Their dark matter became part of larger structures. In this way, great galaxies are partly built from many modest beginnings. Dwarf galaxies also survive as companions, orbiting larger hosts and feeling their tidal pull. They may look faint, but they are scientifically rich because their low mass makes them sensitive to feedback from supernova, gas loss, and dark matter effects. They show that the universe is not assembled only by spectacular giants. Small galaxies help write the architecture of the large. Quasars are powered by feeding supermassive black holes. A quasar looks like a brilliant point of light, but its true engine is a galaxy's central black hole consuming material. As gas spirals inward, it forms a hot accretion disk. Friction, compression, and magnetic processes heat that disk until it releases enormous amounts of radiation. The black hole itself emits no light from within its boundary, but the material falling toward it can become one of the brightest sources in the universe. Quasars are often found at great distances, which means we see them as they were when the universe was younger. They reveal a time when massive black holes were growing rapidly and galaxies were still developing. Some quasars also launch powerful jets, sending energy far beyond their host galaxies. The astonishing part is efficiency. A region smaller than a solar system can outshine a galaxy because gravity near a black hole can convert falling matter into radiation with extraordinary power. Some quasars shine brighter than thousands of galaxies. The most luminous quasars are difficult to comprehend. Their light can cross much of the observable universe and still be detected by our instruments. Although they appear star-like through small telescopes, they are not stars at all. They are active galactic nuclei blazing from the centers of distant galaxies. Their brightness comes from matter falling into supermassive black holes at tremendous rates. In the most extreme cases, the output can exceed that of thousands of ordinary galaxies combined. This allows astronomers to use quasars as backlights. As their light travels toward us, it passes through gas clouds, revealing the composition and distribution of matter across cosmic history. Quasars are therefore both objects of study and tools for studying everything between them and Earth. Their brilliance tells a story of appetite, gravity, and early galaxy growth. A tiny central region can become a lamp bright enough to illuminate the deep past. Black holes grow by consuming gas, dust, and stars. A black hole increases its mass when material crosses its event horizon, but the path inward is rarely simple. Gas may spiral into a disk, heating as it loses energy. Dust can be dragged inward after collisions, and turbulence strip away its orbital support. Stars that pass too close can be torn apart by tidal forces, creating luminous flares as their material streams around the black hole. In crowded galactic centers, black holes can also grow through mergers with other black holes. The feeding process can be messy and episodic. Long periods of calm may be interrupted by bursts of activity when fresh material arrives. Some black holes remain nearly invisible because little matter is falling in. Others become powerful engines, lighting their surroundings as they feed. Growth is not just a matter of swallowing. Before material disappears, it can release radiation, drive winds, and influence the evolution of the galaxy around it. Nothing can escape once it crosses a black hole's horizon. The boundary around a black hole is not a surface you could stand on. It is a point of no return in space-time. Outside it, escape may still be possible if something moves fast enough in the right direction. Inside it, every future path leads deeper inward. Even light, the fastest thing in the universe, cannot climb back out. This is why the boundary appears black. The event horizon is defined not by material, but by causality. It separates events that can still send signals to the outside universe from events that cannot. To someone falling across it in a very large black hole, there might be no sudden wall or flash at the crossing. Yet from then on, returning would be as impossible as traveling into yesterday. The power of this idea is unsettling and beautiful. A black hole is not merely a dense object. It is a region where escape itself stops being part of the future. Black holes can fling jets across intergalactic space. Some feeding black holes do more than swallow. They launch narrow beams of particles and radiation that can stretch far beyond their galaxies. These jets are thought to arise from magnetic fields twisted by rotating accretion disks and spinning black holes. Material near the center becomes organized and accelerated outward at speeds close to light. The jets can punch through surrounding gas, inflate vast bubbles, and deposit energy into galaxy clusters. In radio telescopes, they can appear as enormous structures extending across distances larger than the visible galaxy that hosts them. This feedback can influence whether gas cools enough to form new stars, making black holes important in galactic evolution. The paradox is striking. An object famous for trapping light can also help create some of the largest visible outflows in the cosmos. A black hole's immediate boundary allows no escape, yet the environment around it can launch matter across intergalactic distances. Hawking radiation suggests black holes may slowly evaporate. Black holes seem like perfect traps, but quantum physics gives them a strange, fragile leak. In the 1970s, Stephen Hawking showed that the boundary around a black hole is not completely silent. Quantum fields near that edge can produce a tiny glow, now called Hawking radiation. For large black holes, this radiation is incredibly weak, far colder than the cosmic background around them, so they absorb more energy than they lose. But in principle, if the universe lasts long enough and becomes cold enough, a black hole can slowly shrink. The smaller it gets, the warmer it becomes, and the faster the process continues. This does not mean black holes vanish quickly. Stellar and supermassive black holes would survive for timescales so vast they make the current age of the universe seem brief. Yet the idea is profound. Even the darkest objects may not be eternal. Gravity, quantum theory, and time together may give black holes a final ending. Gravitational waves are ripples traveling through space-time itself. When massive objects accelerate in extreme ways, they can disturb the very structure of space and time. These disturbances spread outward at the speed of light, carrying information from events that may produce little or no ordinary light. The effect is incredibly small by the time it reaches Earth. A passing wave can stretch and squeeze a detector by less than the width of a proton. Yet that tiny change is enough to reveal some of the most powerful events in the universe. Scientists detect these waves with long laser instruments that measure distance with astonishing precision. What they record is not sound in space, but a pattern that can be translated into a rising tone. In that signal, researchers can learn the masses, spins, and distance of the objects involved. It is a new kind of astronomy. Instead of only looking at the cosmos, we can now feel its deepest vibrations passing through our planet. Colliding black holes confirmed a prediction made by Einstein. For a century, general relativity suggested that violent motions in gravity should send waves through space-time. The mathematics was elegant, but the signal seemed almost impossibly difficult to catch. Then, detectors on Earth recorded a brief rising chirp from two black holes spiraling together. The pattern matched Einstein's theory with remarkable accuracy. In less than a second, the objects lost a huge amount of energy as gravitational waves and then settled into one larger black hole. No telescope saw the event in ordinary light. It was discovered through the shape of space-time changing here on Earth. This was more than a technical triumph. It proved that black holes can merge, that space-time can carry waves, and that the universe can be studied through gravity itself. The signal came from a collision that happened long before humans existed. Yet it crossed the cosmos and arrived as a tiny movement in a human-built instrument. Massive objects bend light and create cosmic magnifying glasses. Gravity does not only pull on planets and stars. It also changes the path of light. When light from a distant object passes near a massive galaxy or cluster, its route can curve on the way to us. The foreground mass acts like a natural lens, bending and sometimes amplifying the background image. This can produce arcs, rings, or multiple images of the same distant galaxy. The effect is not an optical trick caused by glass. It is the geometry of space-time revealing itself. Astronomers use this bending to study objects that would otherwise be too faint to detect. They also use it to measure mass, including dark matter that gives off no light of its own. A cosmic lens can turn an ordinary patch of sky into a deep observatory. It lets the universe help us see itself. Gravity becomes a telescope, built not by hands, but by the weight of galaxies. Gravitational lensing lets us see galaxies behind other galaxies. Sometimes a massive foreground object lines up with a far more distant galaxy behind it. Instead of hiding the background galaxy completely, the foreground gravity can bend its light around the obstacle and send it toward us. The result may be a stretched arc, or even a near-perfect ring. This means astronomers can study galaxies that would normally be too dim, too small, or too remote for direct observation. Lensing can reveal young galaxies from earlier cosmic times and help scientists inspect their structure in unusual detail. It also allows researchers to map invisible mass because the amount of bending depends on total gravity, not just visible stars. In some deep images, the most delicate curved smears are among the most valuable features. They are magnified messages from behind cosmic barriers. The universe does not merely block our view. Under the right alignment, it folds light around the obstruction and hands us a hidden background. Dark matter reveals itself through gravity, not light. No telescope has ever seen dark matter shining. It does not appear to absorb, reflect, or emit ordinary light in any familiar way. Yet its gravitational effects show up again and again. Galaxies rotate as if they contain far more mass than their visible stars and gas can explain. Galaxy clusters bend background light more strongly than their luminous matter predicts. Large-scale cosmic patterns also fit best when an unseen form of matter helps pull structures together. This hidden component is not a small correction. It appears to outweigh ordinary matter by a wide margin. Scientists do not yet know what particles make it up, or whether the final answer will involve something even stranger. But the evidence from gravity is difficult to ignore. Dark matter is like an invisible scaffolding for cosmic structure. We cannot see the material directly, but we can trace the way the universe moves around it. Galaxies spin too fast without unseen mass holding them together. In the outer regions of spiral galaxies, stars and gas move at speeds that surprised astronomers. Based only on the visible matter, those outer parts should orbit more slowly, and some material might not remain bound. Instead, rotation curves often stay flatter than expected, meaning stars far from the center keep moving quickly. The simplest explanation is that galaxies sit inside extended halos of unseen mass. This dark matter adds gravity without adding light, keeping the system together and shaping its motion. The discovery changed astronomy because it showed that the bright disk of a galaxy is not the whole galaxy. What we photograph is only the visible portion embedded inside a larger gravitational structure. The evidence is not based on one galaxy alone. Similar patterns appear across many systems. Each spinning disk becomes a clue. The outer stars are not just orbiting beautifully. They are revealing the presence of something hidden. Dark energy appears to accelerate the expansion of the universe. For much of the 20th century, many scientists expected gravity to slow cosmic expansion over time. Matter attracts matter, so it seemed natural that the stretching of space should gradually lose pace. Then observations of distant stellar explosions showed something unexpected. The expansion was not merely continuing. It appeared to be accelerating. To describe this, cosmologists use the term dark energy. It is not a substance in the ordinary sense that has been collected in a laboratory. It is a name for whatever is driving this large-scale acceleration. It may be related to the energy of empty space, or it may point toward new physics beyond current models. The discovery reshaped our picture of the universe's fate. Gravity gathers matter into galaxies and clusters, but on the largest scales, another influence seems to push expansion onward. The cosmos is not simply coasting from its beginning. Something mysterious appears to be changing its speed. The universe's expansion is faster today than long ago. Light from distant objects carries a record of how space has changed while that light was traveling. By comparing distance and redshift, astronomers can reconstruct the expansion history of the cosmos. The result is astonishing. In the early universe, matter had a stronger slowing influence because matter was closer together and gravity mattered more across large regions. Later, as space expanded and matter became more spread out, the effect associated with dark energy became dominant. The expansion began accelerating. This does not mean every object is flying faster through local space. Nearby galaxies, stars, planets, and people are still governed mainly by local gravity and other forces. The acceleration shows up across enormous cosmic distances, where the stretching of space itself becomes the important story. The universe has changed phases in its behavior. It was once slowed by the pull of matter, but today its largest scale growth is being driven onward. scientists still do not know what dark energy is. The name sounds confident, but it is really a placeholder for a profound mystery. Dark energy explains observations in the sense that it fits the accelerating expansion, but its underlying nature remains unknown. One possibility is the cosmological constant, an energy built into empty space itself. Another possibility is that some dynamic field changes over time. A more radical option is that gravity behaves differently on the largest scales than our current theory suggests. Each idea has consequences, and astronomers test them by measuring supernova, galaxy clustering, gravitational lensing, and ancient background radiation. So far, the simplest model works surprisingly well. But working well is not the same as being fully understood. The mystery matters because dark energy appears to dominate the total energy content of the universe. The largest ingredient in cosmic evolution may be something we cannot yet explain. It is a reminder that the universe can be measured with precision and still remain deeply unknown. The cosmic web links galaxies in immense, invisible structures. On the largest scales, galaxies are not scattered randomly like dust. They gather along vast filaments, walls, and knots, with enormous empty regions between them. This pattern is called the cosmic web. It formed as gravity amplified tiny early differences in density. Dark matter created the underlying framework, and ordinary matter followed, cooling into galaxies where the web became dense enough. Galaxy clusters sit at intersections like bright cities, while filaments stretch between them across distances so large that light needs millions of years to cross. Much of the web is difficult to see directly because its gas can be thin and faint. Astronomers map it through galaxy positions, lensing and absorption lines in distant light. The result is one of the grandest structures known. The universe is not a simple sea of galaxies. It is a connected network, shaped by gravity over billions of years, with luminous matter tracing hidden architecture. Galaxy clusters are the largest bound structures in the universe. A galaxy cluster can contain hundreds or thousands of galaxies, all held together by gravity. But the galaxies themselves are only part of the story. Clusters also contain huge amounts of hot gas that glows in X-rays, along with even more dark matter that dominates the total mass. Inside these systems, galaxies move through a shared gravitational field at high speeds. Some collide or lose gas as they pass through the cluster environment. The hot gas between them can reach temperatures of millions of degrees, making the space inside a cluster far from empty. Clusters are important because they sit at the densest knots of the cosmic web. Their growth records how structure formed across cosmic history. They also act as powerful gravitational lenses, magnifying objects behind them. Although larger patterns exist, they are not usually bound as single, stable systems. A cluster is a true cosmic metropolis, gathered and held by gravity. Empty cosmic voids can stretch across hundreds of millions of light years. Between the bright threads of the cosmic web lie enormous regions with relatively few galaxies. These voids are not perfectly empty, but compared with clusters and filaments, they are sparse and faint. Their scale is difficult to imagine. Some extend across hundreds of millions of light years, making them among the largest features in the universe. Voids grew because matter flowed away from less dense regions toward denser ones under gravity. Over time, the rich regions became richer, while the underdense regions became emptier. Studying voids helps scientists test cosmology because their shapes and distribution depend on gravity, dark matter, and dark energy. They are not simply blank spaces. They are important parts of the pattern. A void can reveal how the universe expands and how matter gathers. The absence of galaxies becomes a measurement. In cosmic cartography, emptiness has structure history, and meaning. The observable universe is limited by the travel time of light. There is a horizon beyond which we cannot see, not because there is a wall, but because light from farther regions has not had enough time to reach us. The universe has a finite age, and light travels at a finite speed. This creates the observable universe, the portion from which signals have arrived since the earliest times we can observe. Because space has expanded while that light was traveling, the current distance to those regions is much larger than a simple light travel time might suggest. The boundary is therefore not an edge of all reality. It is an edge of visibility. Observers in a galaxy far beyond our horizon would have their own observable universe, centered on themselves, with a different set of visible regions. This idea is humbling. Our cosmic map is vast, but it is not the whole territory. It is the part of the universe old light has managed to reveal. The whole universe may be far larger than we can observe. Everything we can measure directly belongs to the observable universe, but there may be far more beyond it. The regions hidden past our horizon are not necessarily different in kind. They may contain more galaxies, more clusters, and more empty spaces, continuing in patterns similar to what we see. Or the larger universe could have features beyond our current reach. Because no signal from those regions has arrived, direct knowledge is impossible for now. Scientists infer possibilities from the geometry, uniformity, and expansion history of the visible cosmos. Measurements suggest space is very close to flat on large scales, which could mean the whole universe is enormous compared with the part we observe. It might even be infinite. The thought changes how we understand cosmic scale. The observable universe already contains staggering numbers of galaxies, yet it may be only a local window. We might live inside a visible patch of something far grander. Space might continue forever beyond our cosmic horizon. If space is infinite, then traveling outward would never bring you to a final boundary. There would always be more distance ahead. This is difficult for the human mind because everyday objects have edges. Rooms end, roads end, maps have borders. Space may not. The cosmic horizon limits what we can see, but it does not prove there is an outer wall beyond it. Current observations are consistent with a universe that is flat or nearly flat on large scales, which leaves open the possibility of endless extent. An infinite universe raises strange questions. It could contain regions forever beyond communication, and perhaps arrangements of matter repeated in unimaginable ways, although such ideas remain speculative. What matters most is the distinction between what exists and what can be observed. The edge of our vision is not necessarily the edge of reality. The universe may continue past every reachable signal without asking our intuition for permission. The universe may have no center and no outer edge. Expansion can make it seem as though there should be a middle point from which everything is moving away. But in modern cosmology, the expansion of space happens everywhere. On large scales, every observer in every distant galaxy would see other faraway galaxies receding in much the same way. This does not require a central location. It is a property of the geometry of space itself. The absence of an edge is equally important. The universe might be infinite, or it might be finite, in a curved way that has no boundary, somewhat like the surface of Earth has no edge, even though it has a finite area. That analogy is limited, but it helps loosen the everyday expectation of borders. The universe does not need to be expanding into something outside itself. Space can change its own scale. The deepest map of everything may have no center marked on it, and no rim where the story stops. Cosmic background radiation shows the universe was once nearly uniform. The ancient microwave glow arriving from all directions is astonishingly smooth. its temperature is almost the same wherever we look, differing only by tiny amounts. That smoothness tells scientists that the early universe was once extraordinarily uniform across vast regions. This is one reason inflation became such an attractive idea, because it offers a way to explain how distant regions could share such similar conditions. Yet the glow is not perfectly identical. Its small variations are crucial. They reveal slightly denser and slightly thinner regions that later grew into the cosmic web. Satellites have mapped this radiation in exquisite detail, turning faint temperature patterns into a precise record of the young universe. The background is not a picture of stars or galaxies. It comes from before those structures existed. It shows the cosmos at a stage when matter and radiation were closely linked, and when the future architecture of everything was only beginning to appear. Tiny temperature differences in ancient light mapped future structure. The oldest light carries a pattern of slight warm and cool spots. These differences are incredibly small, but they are not random noise. They reflect variations in density, motion, and sound waves in the hot early plasma. Where matter was a little denser, gravity had a slight advantage. Over time, those regions drew in more material and became the starting points for galaxies and clusters. Less dense regions became the beginnings of voids. By studying the pattern, scientists can measure the age, composition, geometry, and expansion history of the universe. It is one of the most information-rich signals in all of science. The temperature differences are like a blueprint, but not a fixed plan. They are the initial conditions from which gravity built structure. When astronomers compare this ancient map with modern galaxy surveys, they see a remarkable connection. The universe's enormous architecture grew from faint marks in its earliest visible light. Telescopes are time machines because light needs time to arrive. Every view into space is also a view into earlier moments. The farther away an object is, the longer its light has traveled before reaching us. A nearby star is seen as it was years ago. A distant galaxy is seen as it was millions or billions of years ago. This turns astronomy into history, conducted with photons. Telescopes do not simply magnify distant places. They collect old light, preserving the appearance of objects at the moment that light began its journey. Because of this, astronomers can study how galaxies looked when the universe was young, then compare them with nearer galaxies seen at later stages. No human machine can travel backward in time, but light naturally carries the past forward. When a detector records a faint signal from deep space, it is catching a message that crossed expanding space for ages. The telescope becomes an instrument for reading time as well as distance. James Webb can study galaxies from the universe's early childhood. The James Webb Space Telescope was designed to see infrared light with exceptional sensitivity. This matters because light from very distant galaxies is stretched by cosmic expansion, shifting from visible and ultraviolet wavelengths into infrared by the time it reaches us. Webb can peer through some cosmic dust, study faint early galaxies, and examine the glow of stars that formed when the universe was much younger. Its large mirror and cold instruments allow it to detect signals that earlier telescopes struggled to reach. Webb has already revealed distant galaxies with surprising detail, raising new questions about how quickly structure formed. It does not see the absolute beginning, because there was a time before stars and galaxies. But it can observe deep into the era when the first generations of galaxies were growing. In doing so, it helps turn the early universe from a theoretical chapter into a field of visible evidence. The first galaxies were smaller and more chaotic than today's. Early galaxies did not usually resemble the large, graceful spirals familiar from modern telescope images. Many were smaller, clumpier, and more irregular, because they were still assembling. Gas was abundant, mergers were more common, and bursts of star formation could light up compact regions with intense energy. Over time, smaller systems combined, gathered more material, and developed larger structures. Some became disks. Others were reshaped by collisions into more rounded forms. Studying early galaxies lets astronomers watch this growth in progress. Their light often shows hot young stars, disturbed shapes, and chemical compositions less enriched than those of later galaxies. They are not primitive in a dismissive sense. They are young systems in a universe that was still building its architecture. Looking at them is like seeing cities before roads are finished, before neighborhoods settle, before the skyline takes its familiar form. The mature universe grew out of these restless beginnings. Heavy elements became more common with every generation of stars. The universe began with very few kinds of atoms. Stars changed that through their lives and deaths, then passed enriched material into space. Later stars formed from gas that already contained more complex elements than the generation before. Astronomers call this increasing abundance metallicity. It is a record of cosmic recycling. The oldest stars usually contain fewer heavy elements, while younger stars can carry richer chemical mixtures. This matters for planets because rocky bodies need elements such as silicon, iron, magnesium, and oxygen in the right forms. It also matters for biology, which depends on carbon, nitrogen, phosphorus, sulfur, and many other ingredients made or distributed by stars. Each stellar generation adds to the available inventory. The universe did not become chemically rich in one event. It became richer through repeated cycles of birth, burning, release, and renewal. Every later star system carries some memory of the stars that came before it. Planet formation became easier after stars enriched the universe. The first star-forming regions had little more than hydrogen and helium, so building rocky planets would have been difficult or impossible there. Solid grains need heavier elements. Once earlier stars released those ingredients into space, future clouds had more material that could condense into dust. Dust is crucial because it helps gas cool and provides the tiny solid particles that can grow into planetesimals. As galaxies aged and became chemically enriched, the conditions for making rocky worlds improved. This does not mean planets were absent in all early times, but their composition and frequency likely changed as the universe matured. Giant planets also depend on solid cores or icy materials in many formation models, so enrichment affects them too. Planet formation is therefore tied to the broader story of stellar generations. Worlds are not just byproducts of stars. They are signs that the universe has processed enough matter to make solid complexity possible. Life required cosmic chemistry that did not exist at the beginning. The early universe could not have produced life as we understand it. It lacked the needed chemical variety. There were no carbon-rich planets, no liquid water oceans, no phosphorus in rocks, and no stable environments around long-lived stars at first. The ingredients had to be made, spread, gathered, and assembled across immense time. Carbon chemistry became possible only after stars produced carbon. Rocky surfaces required heavy elements. Water needed oxygen as well as hydrogen. Stable planetary systems needed disks enriched with dust and minerals. Even then, chemistry had to find the right settings, with energy sources and conditions that allowed complexity to grow. This makes life a late developing expression of cosmic history. It is not separate from the universe. It depends on the universe becoming chemically mature enough to support it. The first moments gave us physical laws and simple matter. Only later did those laws build the ingredients that could become biology. Earth's atoms have belonged to many earlier cosmic stories. The matter in our planet did not begin with Earth. Its atoms passed through earlier stages of the galaxy before becoming part of this world. Some were made in ancient stars. Some drifted through interstellar clouds. Some became dust grains that traveled through cold space before joining the solar system's birth cloud. Others were locked into asteroids, melted inside young bodies, or rearranged during impacts. By the time Earth formed, its ingredients had already lived through a long sequence of cosmic environments. Even after the planet assembled, atoms continued changing homes through geology, oceans, atmosphere, and life. The same carbon atom might move from air to leaf to soil to sea over time. On a deeper scale, every atom here carries a pre-Earth past. Our planet is not made of new material. It is a temporary arrangement of ancient matter, gathered into a world that keeps transforming its inherited pieces. Human eyes see starlight that began traveling before civilization. When you look at the night sky, you are receiving signals from many different times. Some stars are close enough that their light left after modern history began. Others are so far away that their light began traveling before writing, agriculture, or the first cities. The star may have changed during that journey, but your eye receives the older message. This gives ordinary stargazing a hidden depth. A point of light is not merely a distant object. It is an arrival from the past. The human eye can see only a limited number of stars under dark skies, yet even that modest view connects us with timescales far beyond a human life. Telescopes deepen the effect, but the principle is already present when you look up unaided. The night sky is layered with delayed arrivals. Some of its light crossed space while generations rose and vanished on Earth, and only now reaches a living retina. The night sky shows only a tiny fraction of all stars. Even under excellent dark skies, the unaided eye sees only a few thousand stars at most. That feels like abundance, but it is almost nothing compared with the population of our galaxy, let alone the wider universe. Most stars are too faint, too distant, or hidden behind dust. Many are small red dwarfs that shine weakly compared with the brighter stars that dominate familiar constellations. Our view is also limited by Earth's atmosphere, city lights, and our position inside the galactic disk. The stars we recognize are a local and biased sample. They are not a complete portrait of the Milky Way. With telescopes, the sky opens into richer layers, revealing star fields, clusters, and galaxies beyond normal sight. Yet even the deepest images cover tiny patches. The darkness between visible stars is not emptiness. It is mostly limitation. The sky contains far more light than our eyes can gather. The universe creates complexity from simple laws and tiny beginnings. One of the great wonders of science is that immense richness can arise from simple rules. Gravity pulls matter together. Nuclear forces shape atomic cores. Electromagnetism governs light, chemistry, and charged particles. From these basic interactions came clouds, stars, planets, oceans, minerals, and living cells. The early universe did not need to contain finished complexity. It needed conditions that allowed structure to grow. Tiny differences became large patterns. Simple atoms became heavier elements through stars. Dust became worlds through collisions and gravity. On at least one planet, chemistry became biology, and biology became awareness. This does not make the process easy or inevitable in every place. It makes it more astonishing. The universe began with simplicity at enormous scale, then unfolded into layers of organization. What we call complexity is not separate from physics. It is physics given time, energy, and the chance to build upward from very small beginnings. Far future stars may form from the last remaining gas. Star formation will not continue forever at its present pace. Galaxies need cold gas to make new stars, and that gas is gradually used, heated, expelled, or locked into long-lived objects. In the far future, star birth may become rare, occurring only where remaining gas clouds can still cool and collapse. Some new stars might form after galaxy mergers stir material together. Others could arise from gas returned by aging stars, though in smaller numbers. The final generations may be dominated by small red stars because they require less mass and can burn for extraordinary lengths of time. These late-born stars would appear in a universe already much older, darker, and more spread out than the one we know. They would be like the last candles made from the remaining fuel of galaxies. Star formation is one of the great creative processes in the cosmos, and the future may slowly bring it towards silence. One day, the universe may contain only fading remnants. If current trends continue, the bright age of stars will eventually pass. Massive stars will disappear first, then sun-like stars, then the long-lived red dwarfs after immense spans of time. What remains may be white dwarfs, neutron stars, black holes, cold planets, and scattered debris. Galaxies may grow dim as their luminous populations fade. Some remnants could be ejected into deep space by gravitational encounters. Others may orbit within darkened systems. Over even longer times, black holes may lose mass through Hawking radiation, leaving the universe thinner still. This future is not a sudden apocalypse. It is a gradual fading of activity as usable energy becomes harder to concentrate. The cosmos would still exist, but it would no longer blaze with the same creative intensity. Thinking about that distant ending makes the present era feel extraordinary. We live while stars still shine, galaxies still glow, and the universe is bright enough to know itself. And so, we come to the end of our journey through the story of the universe. We began with the earliest moments science can reach, when space, time, matter, and light were still becoming the cosmos we know. We followed the first atoms into the long darkness before stars, then watched those stars awaken and begin the slow work of creation. From their heat came the elements that would one day shape planets, oceans, mountains, and living bodies. We drifted through galaxies as they formed, merged, and grew. We passed black holes bending time at their edges, dark matter shaping what cannot be seen, and dark energy carrying the universe into a future still filled with mystery. We visited worlds with double suns, hidden oceans, and lonely planets moving through the dark without a star to guide them. And through it all, one idea kept returning. The universe is not only vast, it is connected. The atoms in your body, the light in the sky, and the ground beneath you all belong to one unfolding story. Now, as that story settles, let your thoughts settle with it. Let the scale of the cosmos become soft and distant. Let the stars feel steady above you. Let your breathing slow in its own time. There is nothing more you need to follow now, nothing more you need to hold. If you enjoyed this journey, you are always welcome to like, subscribe, or leave a thought below. It helps other curious souls find their way here too. And if you are still awake, there is another calm science journey waiting for you on the screen. But for now, let the universe drift on without effort. Let your body rest. Let the day fall away. Sleep well and good night.